Okay, today in class we reviewed how to evaluate limits graphically and numerically, and tonight I'm going to give you just a quick review on limits algebraically, and we're going to do some work on it together tomorrow. So please, try to review this and think about what you learned last spring, and then come in tomorrow with questions and ready just to work some problems and remind ourselves, because this is not calculus, but this is going to be necessary for us to learn calculus. So yesterday or today in class we were saying, all right, the limit of f of x as x approaches 2, and we were looking at a graph of f of x and determining what the y value was, or what the y value was approaching as x approached 2. Okay, so f of x, right, we know that just stands for a function. So let's say we actually replace that with a function. So we're going to replace f of x with the function x, or y is equal to x, but I'm not going to put the y equals part. I'm just going to put the part on the right. And so let's say I'm going to find the limit of x as x approaches 2. Well, I could use the same method we went over today. I know what the function y equals x looks like. It's a diagonal line that goes through the origin. And as x approaches 2, here it is over here. Okay, here's the point we're looking at. Y is also approaching 2, and so that's my answer. Right, but what if you're given a limit like the one down here that I don't know what that function looks like? Maybe you do, but I don't, and I don't have my graphing calculator, let's say, and so I'm asking you to find the limit as x approaches 2 of this whole function that I don't know what it looks like, but I'm sure there's some way I can find it, and I'm going to do it algebraically, and that's what we're going to do tonight. So the easiest way, the first thing you should always try is substitution, and so that just means plugging it in. So I'm going to take 2 and I'm going to plug it in everywhere I see x, right, which is essentially what I did up here anyway. I drew the graph, but I could have just plugged in 2 everywhere I saw x and found the same exact answer. So that's what I'm going to do here, and I'm going to get 4 minus 6 plus 2 over 2 minus 1, which is equal to 0 over 1, which reduces to just 0. And that's okay. There's nothing wrong with the answer 0. That is my answer. If I were to graph this function on my calculator, I would find that when x is approaching 2, y is approaching 0. But what if I were to give you the limit as x approaches 1 of x squared minus 1 over x minus 1? Again, first thing I should always try is plugging in. I plug it in and I get 0 over 0. Okay, so this is bad, right? So that's an indeterminate form. But do not just write DNE and walk away. That is really bad, even worse than the 0 over 0. So if I plug in and I get something like that, 0 over 0 or something over 0, I should not write DNE. Instead, I should evaluate the limit by factoring. So again, this hopefully is review. But so if I gave this is the same problem that I had above. I'm going to change colors here. So what I'm going to do is I'm going to factor, and luckily we know how to factor this. I've got x minus 1, x plus 1, but do not write that this limit is equal to just the function factored. It's equal to the limit. I need to keep my limit notation, right? Notation is important. I'm still trying to find the limit as x approaches 1, but now I've just rewritten the function as x minus 1 over x plus 1, times x plus 1 over x minus 1. Well, hopefully you notice I can now cancel out my x minus 1s, and so now I can just go back to substitutions. I'm going to take my, as x approaches 1, plug it in right here for x, and find that my answer is 2. So I want you to take a minute to think about, why did I not get an answer at first, but then once I factored, I found an answer? What do I think, without graphing on your graphing calculator, I want you to think about why would that happen? What do we think that graph is looking like around the x value 1? And so we're going to talk about that tomorrow in class. Okay, so we got another problem here. We got x cubed minus 1 over x plus 1, x minus 1. If we plug in 1, we already know without even writing it down that we're going to get 0 over 0. Do not write DNE, but I'm going to factor, and if you don't remember how to factor differences of cubes, you need to watch my other video, but I can rewrite this, right, as the limit as x approaches 1 of x minus 1 times x squared plus x plus 1 all over x minus 1, and so I'm going to cancel out my x minus 1s again, and now I can just plug 1 in here. I've got 1 squared plus 1 is equal to 3, right, and my answer is 3. Once again, I got an indeterminate form at first, but then once I factored, I ended with an answer. So what do we think that graph is looking like? Both of these graphs are looking like around x equals 1. Okay, I want you to try this last one on your own. So go ahead and pause the video, try it, and then we'll check our answers. Okay, hopefully you took some time to do that problem and got the answer -2. If not, we'll have plenty of practice tomorrow. And if you weren't sure how to do that one, that looks pretty difficult to factor synthetic division. And so again, that other video that I have on haiku, you could watch that to remind yourself about synthetic division. So when I first tried substitution, obviously I could see that I'm going to have a 0 into the denominator, so I don't have to go any further. I know I need to try to factor. And with synthetic division, because there's an x minus 1 in the denominator, I'm looking for, the only thing that's going to help me out is if I can find an x minus 1 in the numerator. And so I want to use -1 as my factor to try to use synthetic division. But check that video out if you're not so sure about it. Okay, so after factoring, the next thing is if we have one-sided functions or piecewise defined functions, and what are we going to do to be able to evaluate limits algebraically when we're given this type of function. Okay, so my function is f of x. If you don't remember what this is how we write piecewise defined functions, right? So we got f of x is equal to 3 different things in this case. We got x squared minus 2 if x is less than 1. And we're going to say f of x is equal to -1 if 1 is less than x is less than 2. So if x is between 1 and 2. And then f of x is equal to x minus 1 if x is greater than or equal to 2. Okay, so we're going to treat these just like substitution, except where? Okay, hopefully you're thinking except where we change, right? So at the points where our functions change. So except at x is equal to 1, right? And at x is equal to 2. Sorry, my computer's malfunctioning a little bit here. So let's say if I asked you, what's the limit of f of x, this function above, as x approaches 1? And I want you to justify it, right? As we talked yesterday, but justifying involves using our definition of a limit. So I'm going to look at, I'm curious to know what the limit of f of x as x approaches 1 from the left is, and the limit of f of x as x approaches 1 from the right. Okay, so from the left is when we have first function. When I plug in, I'm just going to substitute, right? And so I'm going to plug in 1 there. 1 squared minus 2 is -1. And then the limit of f of x as x approaches 1 from the right, I'm going to use this second function, also equal to -1. Okay, so these are equal, so the limit of f of x as x approaches 1 is just equal to 1, right? That wasn't necessarily going to happen, but in this case it does. The limit does exist, even though it's a piecewise defined function. If I were to ask you what's the limit of f of x as x approaches 0, I'm just going to plug in 0 where it fits, which is x is less than 1, right? And that's just going to be equal to -2. Okay, so I want you to try the limit of f of x as x approaches 2, and I want you to figure out what it is, if it exists, and if it does exist or it doesn't exist, I want you to justify it. Okay, if you haven't paused it, pause it now and do this problem. But if you have, check your answer here. So if I'm looking at the limit of f of x as x approaches 2, I'm interested from the left and from the right. From the left, it's just equal to -1, and from the right, it's equal to +1, right? When I substitute in here, x is greater than or equal to 2, I'm getting +1. They're not equal, so the limit of f of x as x approaches 2 does not exist because the two sides do not equal each other. Okay, next thing we're going to do is look at absolute value functions. Okay, so anytime we have an absolute value function, we're always going to rewrite as a piecewise defined. So rewrite as piecewise, because that's basically what it is, right? So let's say I have the function y is equal to absolute value of x. Pretty basic. Hopefully we all know what that looks like. We've got a v here at the origin. And so really what that is on the right side, right, this is just the function y is equal to x. And on the left side, what is that? That's just y is equal to -x, right? And so they've just switched signs. So I could rewrite this as this is equal to y is equal to +x when x is greater than or equal to 0, and y is equal to -x, right, when x is less than 0. And I can put the equals on either side, up here or down below, but not both places. And so then really anytime I'm looking for a limit, I'm gonna find it just by substitution anywhere except for at 0. I'm going to use my skills I learned just above with piecewise defined. So the first thing you always do is figure out the turning point, right, and then rewrite it as piecewise defined and go from what we learned above. So another example, what if I had y is equal to the absolute value of x minus 1? Okay, so hopefully we have an idea what that looks like. It's moved over to the left, but even if you didn't know that, I know that the turning point is where the function is equal to 0, which is when x is equal to 1. So this is going to be rewritten as y is equal to, it's just itself when x is greater than or equal to 1, but it's the opposite of itself when x is less than 1, right? I could rewrite this right here as 1 minus x if I wanted to, but just so you can see, it's just the opposite of itself when it's to the left of its turning point, if you will. Okay, so I got one more. What if I have y is equal to the absolute value? Let's do this, x minus 1 over the absolute value of x minus 1. Okay, so be careful here. So I want to rewrite it. Right, so I'm going to say y is equal to, it's just itself, right? The turning point, again, is just 1. When that's equal to 1, that's where, and it's actually undefined, but that's where it's changing. So I'm going to say it's x minus 1 over itself, just x minus 1, when x is greater than or equal to 1. But then it's x minus 1 over the opposite of itself, negative x minus 1, when x is less than or equal to 1. And what's interesting here is that this is just equal to 1, right? And this is equal to negative 1. And so I already know that the limit of this function y, this last function y, as x approaches 1, doesn't exist, right? Because coming from the right, it's equal to 1, and coming from the left, it's equal to negative 1. Okay, I want you to try this next one on your own, and so go ahead and pause the video, try this, and we'll check that one tomorrow during class. So the very last thing is radical functions. Okay, so the very first thing with radical functions is I'm always write the domain. So just like last one, I'm going to rewrite as piecewise defined. This one, I'm always going to first write the domain of the function. So for this one, the domain, hopefully we know what the domain is, but since under the radical it has to be positive, I know the domain has to be from 7 to infinity, right? It can include 7 because we can have 0 under the radical. That's fine. We just can't have a negative. So if I were to plug 6 in, again, always just try substitution. I plug in 6 here and I get a negative number. So obviously I know I can't take the square root of a negative number anyway, but if I can go ahead and see once I've written the domain, 6 isn't even in the domain, so this limit doesn't exist because the graph doesn't even exist there. So, but then what if I say the limit as x approaches 7 of this same function, right? So the domain remains the same. This 7 is in the domain, but think about, picture the function, right? So it's, this is what it looks like, and here is x is equal to 7. Does that limit exist? Think back to the definition of a limit. Hopefully you're thinking, no, it doesn't, right? Because it doesn't exist to the left of it, and a limit has to be the same from the left and the right. Since it doesn't exist from the left, this limit itself does not exist. So last one here is the limit as x approaches 5 of square root of x minus 1 minus 2 over x minus 5. We have two restrictions here, right? We've got the square root up top, so I know that my domain has to be greater than or equal to 1. But I also know that my domain cannot equal to 5 because I can't have a 0 in the denominator. So this would be my domain. So I'm trying to find the limit as x approaches 5. Now, if I was trying to find it as x approaches negative 5, obviously I would just say d and e because it's not in the domain. But 5, although it's itself is not included in the domain, the function exists on both sides, so I could have a limit that exists. I know I can't do substitution because if I plug in 5, I'll get a 0 in the denominator. So what I'm going to do is I'm going to rationalize. So whenever we have square root functions where they're in the domain, but I'm getting something with 0 in the denominator, I'm going to rationalize. Hopefully you remember what that means, but I'm just going to multiply by the opposite of this, the reciprocal in a sense. Okay, so the square root of x minus 1 plus 2 over itself. Okay, and we multiply this out, we get x minus 1 minus 4 over, and I'm not going to actually multiply the denominator out, I'm going to write it as it is, because you'll notice that in the numerator I have an x minus 5 that I can cancel out with the denominator, and now I can just plug it in. And so when I plug this in, I get 2 plus 2, and so my answer is 1/4. So tomorrow we will work on more problems like this. I will see you in the morning. Bye.